Right, this presentation deals with simple harmonic motion in the terms of properties of waves and sound waves. And remember that you can always visit sciencewithmrnoon.com and you can see interactive videos, you can see presentations, PowerPoints, interactive labs that you can do, animations that allow you to do interactive stuff, and the online quizzes that help you test the knowledge that you might have obtained from these videos. We had just talked about, last time we talked about simple harmonic motion, and we had talked about simple harmonic motion in a pendulum,
and a mass spring scale.
And a mass spring scale. And now what we have here is we have an action that repeats itself over and over again, and it's this one is going horizontal back and forth, and this one's going vertical up and down. If I had a piece of paper and was to draw it out, like this going back and forth, it would make a curve, yeah. And if I did the same thing here, if I had a piece of paper and I had this marking, like it looked just like a seismograph reading. Mm-hmm. So if I have this, and this is going back and forth, right? So I got this going back and forth, and then I start moving this. And the faster you move it, or the slower it moves back and forth, you get this nice curve, right? If it goes real fast, you get a nice curve to it. It's the same motion here. This is up and down, and if I start moving this, and I keep my marker on a good spot, then you'll get this curve going on as it moves, as you draw it out. Now, if you want to pick this paper up and pull on it for me, we'll do that here. All right. Just start pulling on it. All right. So you see that? Mm-hmm. So you get a curve. I'm just going up and down, but as over time, if you take time into another dimension, if you take time into perspective, then you'll see that these wiggles turn into waves, right? So waves transmit energy but not matter, and ways we can see that, I could take a piece of tape and I could take a little piece of red tape and I could place that little piece of red tape right there on that slinky, right? And if I move this up and down, that red tape will move up and down, but it won't move it won't move with the wave, right? It just moves up and down. It doesn't go from here all the way down and then back to my hand. I can't have the actual tape move down the spring and then back again. It only moves up and down because I'm putting energy into it up and down. Mm-hmm. But the energy does. The energy travels. If I take this nice and tight and I put energy in it, the energy goes all the way down and then comes all the way back. It reflects and comes all the way back. So waves transmit energy but not matter, not the solid matter that makes it up. And we're going to talk about mechanical waves for this session. We're going to talk about sound, and we're going to talk about waves and slinkies. But mechanical waves need a medium. They need something to move through, whether it's solid, liquid, or gas. It has to move through something. All of the waves I'm talking about don't move in the vacuum of space. So if I have this slinky right here,
So that's why light moves in the vacuum of space, because
it's an electromagnetic wave, not a mechanical wave, right? So it's not a mechanical wave. So you can see the slinky, the wave doesn't continue, even though there's air, it doesn't continue. Sound waves won't travel in the vacuum of space. They need to travel through a substance, whether it's solid or liquid or gas.
So technically, in movies, when you hear an explosion in space, you really can't hear that.
Exactly. A transverse wave is when my wave motion, right, I place in is perpendicular to the energy transfer. So my motion goes across the table like a saw this way, and the energy goes all the way down and back again on the table. And that's a transverse wave because it makes this S, right? It makes this S motion to it. And when we look at a transverse wave, the different parts of this transverse wave you see there, we have the crest is what we consider the highest point of the wave, and the trough is what we consider the lowest point, and a wavelength is the point where
It comes back to the.
all right, yeah, wherever your starting reference point is.
So the period.
Wherever your starting reference point is, which we're going to start right here for this one, when it comes back, it completes one cycle back to that point, that's a wavelength. So we could see this S shape would be a wavelength, or if we started right here where it says crest, a wavelength could be from this crest all the way to the top of that crest, or it could be from this trowel all the way to the next trowel. That would be the length of one wave. And we see that with a pendulum. Equilibrium's right here, right? So it goes into equilibrium, and then it goes under equilibrium, and then it goes back up to here. So if I start it all the way up at the crest part, it goes down and then back to the crest, and we have a wavelength.
So it's a period.
Yeah, one time period. The wavelength takes place in one time period. That's correct. And the maximum displacement, what do we call that? Just like we had over here. What was the maximum displacement from equilibrium?
What?
It's a big word. Amplitude?
Oh, but the amplitude doesn't matter.
The amplitude does matter. This is the distance. This is equilibrium. Our straight line is equilibrium, and this crest is the positive amplitude, and this trowel is the negative amplitude. So amplitude is maximum displacement or distance from equilibrium position, either above or below equilibrium.
But I thought you said the amplitude doesn't matter.
Oh, the amplitude didn't matter for the
Pendulum.
time period, the amount of time. I can increase this amplitude, watch. I can go, and it's still the same amount of time. All right, the amplitude doesn't affect the time period, but it does affect things
The
like
wavelength.
when we have sound waves, it affects the amount of energy or intensity of the wave. So if I increase it takes more energy to increase the amplitude. All right, a little energy, little amplitude, a lot of energy, a lot of amplitude. So we do have a relationship there with energy, but the time period it takes, I can go like that with a large amplitude in the same amount of time. So the amplitude doesn't directly correspond to the time period or frequency. Right? It has to do with energy, how much energy is in the system. Right. And now we got transverse waves. Energy is proportional to the amplitude. Oops. Okay. You see that there? The energy is proportional to the amplitude squared for transverse wave. And we see that I got to do the energy. I have to increase the energy on both sides, right? If I increase the amplitude, if I put more energy into it, I have to put more energy on this side and on this side, right? So it's the amplitude squared. Amplitude on top and the amplitude below.
It's like a dilation.
All right, so longitudinal waves. Now longitudinal waves are when the wave motion is in the same direction as the energy motion, right? So the energy travels from this end of the table to that end of the table, and my wave motion is also running parallel to the energy, the direction the energy is going in. So we have the energy going in this direction, and we have the motion of the wave going in this direction. And when I do that, what you see is these little compressions, right? So we have the parts of the wave, we have compressions, and then we have what's called a rarefaction, is the expansion, right? So we have compressions we have expansions going on. Obviously, if this is all attached to itself, if I compress one part of the spring, this has to expand, right? So when I send out a bunch of these, we have compressions and rarefactions taking place on this, all right? So transverse was where we had either up and down or back and forth. We had something that was perpendicular, and longitudinal is when the energy and the motion goes, the length kind of goes off on the length of it, all right? Okay. And the wavelength here is what we see
From one,
is,
the beginning of a compression to the beginning of the next one?
Yep, you have to, you could do it just like you did with the wave, where you can have 2 points where you repeat the motion. So sometimes you can have the middle of the compression to the middle of the compression, or you can have the end of the compression to the end of the compression, but you just have to stay consistent with your marks.
Could you do it from a rarefaction too?
Yeah. If we have here, you know, what we see is a diagram. So if we had a test, we had a diagram. You could do it from the center between these two to the center between these two. That would be, you would notice that all these are the same measurable length. Right, and this is a symbol. Lambda represents wavelength. If you look on your New York State Physics reference table, under properties of waves, they have this little lambda that says wavelength. Wavelength is a distance or displacement. All right, so a pulse is a single vibration. So I have I could do a longitudinal pulse, just one, or I could do a single. I could do a single pulse, just one, that's transverse. And a periodic wave is a repeated, just like simple harmonic motion, right? See, I keep repeating it over and over again? That is a periodic wave is a repeated motion over and over and over and over. All right, so this is the fixed position. So if I put a pulse going up, just like in the picture, I should get a pulse going down, right?
Yep.
So now it's saying, what if happens if I loosen this? That allows the spring to move up and down. So this is got a ring on it, and you can see it goes up. So it's loose. So if I send that same pulse down, what's going to happen?
It's going to come back on the same side.
On the top. So if I do it up, it should come back on the top. Come back further. All right, let's see. So it comes back on top. Can you see that kind of?
Is it? Yeah, I can see it.
So when we have a loop, then we have it come through, and because it's free, we'll get a reverse velocity, but we'll get the same amplitude. Now what we're going to do is we're going to look at what's called interference. And this is when two waves, they occupy the same space at the same time. So it's called interference. When this happens.
They'll just rebound off each other and come back, won't they?
Well, let's see. Do a pulse. Do something just like that. So do one pulse. All right. I'm going to say 3 and then do that again. Okay. 1, 2, 3. All right. So what happened?
They stay on the same side too.
They stay on the same side, but they get larger, don't they? Try it again. 1, 2, 3. Right when they occupy the same space, do they get larger?
It becomes one wave, and then it comes
One
back.
big one, and then they actually go right through each other. So I'll just put this up here. That's called constructive interference, and that's when you see two waves are coming together. At the point they come together, they add to each other. So this point is this wave amplitude plus that wave amplitude.
It's just like a tidal wave.
At the same instant, exactly. So then we got, then they separate. So on the other side, we see that this wave is over here, continuing in its motion, and the smaller wave is over here, continuing its motion.
Oh, so they don't rebound and come
Yeah,
back.
they don't bounce off each other. We do that, do a little wave, just do a little one. There you go. And I'm gonna do a large one, so I'll go 1, 2, 3. You see the big one continues all the way down there, and the little one continues in this direction. At the points where they meet, they get larger. So now what I'm gonna have you do is I'm gonna have you continue like you're doing. I'm gonna do in the opposite direction. This is called destructive interference. All right, it's we have two waves in the opposite direction. All right, you're going to have an amplitude like you had before that's positive, and I'm going to make a negative amplitude. So ready? 1, 2, 3. All right, and when they come together, you want to 1, 2, 3. They cancel each other out at that instant.
So it's nothing. It's just 0.
If they're equal to each other, there's nothing. If one's larger than the other, then you subtract the two at that point. All right, so wave interference, two waves, unlike two objects that are solid matter, being pure energy and not the matter, can occupy the same place at the same time. This condition is called interference. And then we have the two types of interference, constructive interference, where displacements are in the amplitudes are in the same direction. And when they come together, they add to each other, or destructive interference when they subtract from each other when they come together. All right, so wave velocity. This is a simple equation that's on our physics reference table, is that the velocity is equal to lambda over time period t. Now this is the same equation we've been using since the beginning of the year, where velocity is distance or displacement over time. Our distance is wavelength. That's the distance of a wave, and the amount of time it takes to travel that cycle is the time period, capital T. So we're really using the same equation we had before, where we distance over time, except now we're referring the distance to wavelength and the time to that time period it takes to go through that cycle. So now our frequency is the inverse of the time period. So since we have lambda over t, we have frequency times lambda is equal to velocity also. So if we're given a frequency, that's the inverse of the time period. If we're given a time period, that's the inverse of the frequency. They're inverse of each other, right?
So if we are given the frequency, then velocity is it's velocity lambda equals f.
F equals 1 over t. So we got that 1 over t, or capital T equals 1 over f.
Mm-hmm.
So you could have wrote this lambda 1 over f, but then of course you'd have lambda over 1 times f, which would be what you have there. All right, simple enough? All right, so we have velocity is meters per second, lambda is meters, time is in seconds, and frequency is in hertz. Or it could also be oscillations per second, but we're commonly. All right, so we have a water wave, has a wavelength of 8.5 meters. It washes past the boat at anchor every 4.75 seconds. What is the wave's velocity? All right, so velocity is wavelength over time period. Our wavelength is 8.5 meters. Our time period is 4.75 seconds. And we have 1.8 meters per second as our answer for the wave velocity. All right, so we have the velocity of any mechanical wave depends on a bunch of properties that are in the medium, such as the density of the medium, the temperature, right? Temperature has a relationship. The tension in a string, water, waves in water, how much, what the depth is relevant to the pressure that water is under, and that is relative to the density of the water, right? As you go down in the ocean, the water is denser because of all the pressure above it. And the type of material. And we have a equation for sound waves that if at standard room temperature, sound travels at a constant rate, which is given to us in our physics reference table as 331 meters per second for the velocity. All right, if you raise or lower the temperature, you change that by 0.6. whatever
Wait,
the degrees of
T
temperature.
equals temperature?
Yes. All right, so standing waves. All right, I'll do this one. You can move a wave across a medium, right, like that. But if I get it in its, if I get it to a point where the wave going down equals the wave coming back, right? Then you'll see right in the middle, it looks like it's not moving very far. It has minimum displacement from the equilibrium position. That's called a node, N-O-D-E. These maximum displacements are called antinodes. And this is called a standing wave because it just kind of, you know, looks like it's...
So at those peaks, those are the antinodes?
Yep, the peaks and low...
In the troughs?
Yep. It's called a standing wave because it looks like it's not moving to the left or the right, right? It looks like it's just standing in the same spot, but it's still a wave motion. It's oscillating. It's got a simple harmonic motion. So what I just showed you there, this is obviously one wavelength. From me to that metal rod over there is the wavelength, right? The distance between me and that rod is the length of this wave. If I have only this part of the wave though, like what you see up there, if I have a wave that, all right, how much of the wavelength is this?
Half.
Half, very good. So this is called the first harmonic. All right? And it's half the wavelength, or 2 times the length between me and the pole gives you the wavelength, lambda, of the first harmonic. And n is the number of antinodes. There's one antinode present.
Oh.
So that's what n represents. So now this was, there's 2 antinodes. This is the second harmonic. And we talked about this, that when I do this, all right, this is the length from me to the pole is the wavelength. So L, my length from here to there, is equal to the lambda, the wavelength. And there's 2, n equals 2 antinodes. It's the second harmonic. So now we have this guy. All right. You see 3 antinodes, right?
Wow.
And what's the wavelength here? Or my length is what compared? There's 1.5 wavelengths is what you see with these 3 nodes.
So that's half L? Or
So 2 out of the 3 nodes, right? There's 3 antinodes. Now you got me doing that. There's 3 antinodes, and 2 of them. So 2/3 of this entire length is the wavelength.
oh, okay.
All right. So now we got 4 antinodes, and that's 1/2 the length. So. You see that? All right, so you had 4 of these antinodes, and one wavelength is half of the entire length. So here's our equation. We only want 2 of the antinodes, no matter what the length is, or no matter what the number is of antinodes. N represents the number of antinodes, and only 2 of them are the wavelength. So 2 times the entire length divided by the number of antinodes gives us the wavelength. All right, so we've got a question here. Waves travel along a 96.1 centimeter guitar string at 492 meters per second. Find the fundamental frequency of the string. here's my giant guitar, and from my hand to that pole is the length of the guitar string, 490 or 96.1 centimeters. How do you play a guitar? Do you go like this, or do you go? Pow, pow, pow? So when you plug a guitar string, it goes like this.
So,
Look, it goes like this. This is how a guitar string vibrates when you pluck it. So how is this related to the wavelength? Now you want to know what the wavelength is, right?
it's two of those.
So twice this. Twice the length.
So then it's not 96.1.
So how many antinodes are there?
There's one.
1. So 2L divided by 1. Right, so you find the wavelength, but what we're looking for is the frequency. And we had our equation that wave speed is equal to the frequency times lambda, which is the wavelength. What's the wave speed? How do we find that?
The speed is in the velocity.
Yeah.
It gives it to you.
Good. 492 meters per second. So we have our speed divided by our lambda, 492 divided by 1.922 meters. And that gives us our fundamental frequency, 256 hertz, or cycles per second, or vibrations per second in a guitar. Find the frequency of the fifth harmonic. So our fifth harmonic is, we have N is 5. And we find the wavelength in the fifth harmonic, and we use the same velocity, and we determine that it's a frequency of 1,280 hertz.